All right, so what we're going to do now is we're going to set up basically our next big idea in physics. So we're going to use the work-energy theorem to build to talking about our energy balance equation and then to talk about conservation of energy. So this is sort of all tied up with our second big problem in introductory level physics. We said our first big problem was Newton's second law. Our next big problem is going to be working work-energy theorem problems, conservation of energy problems. We'll talk about how those are similar and the little distinctions between them, between each type. So to do this, let's start by talking about the net work. And so what we want to do is we want to emphasize what do we mean when we throw net out in front. So the net work is a way of saying the work done on the object by all the forces acting on the object. So this is like when we talked about the net force, we said the net force is the sum of all the forces. So one of the ways that we can talk about the net work, right, there are three of them, but the first one is that we can say that the net work is simply the sum of the work done by all the individual forces. So we would find the net force by doing the summation of all the forces. One way to get the net work is simply to add up all the work. So if you've got forces 1, 2, 3, however many are acting on your object, the net work is simply the work done by force 1 plus the work done by force 2 plus the work done by force 3 plus however many other work terms you've got. Now the nice thing about this, the net force, because forces were vectors, the net force is a vector summation. Work is a scalar. So the net work, as we're calculating it here, this is literally just add up a series of numbers. So you'll have some number for the work done by force 1, another number for the work done by force 2, another number for the work done by force 3. Just add all those numbers together. Now, the second way that I can think about the net work is it's the work done by the net force. So you notice that here I'm basically choosing to do my vector summation first and then stick that inside an integral. That sounds like a much more complicated process, which is why as a general rule we're not going to approach doing actual calculations for the network this way. There will be some special circumstances when we know something special about the net force. Usually it's equal to 0 when this will be useful. But as a general rule, we're almost always going to calculate the net work by simply adding together these individual work terms. But there is something useful that I can do with this particular expression. So one thing I'll do is I'll just, instead of dealing with this as, so my dot product says this is really three terms here, right? I've got an integral over the x component of the net force times dx from some initial to final position in x, that's what I've got here, plus there's a second integral for all that in y, plus a third integral for all that in z. We're just going to say it doesn't change the answer, so let's just worry about doing a single dimensional problem where we're only moving back and forth on the x-axis, and then we'll get to the right answer even if we're not including those two additional terms. So here's the net work done in a one-dimensional problem. Well, I know from Newton's second law that the net work is equal to mass times the acceleration. So if I want the x component of, or I know that the net force is equal to mass times acceleration. So if I want the x component of the net force, then I need mass times the x component of the acceleration. And from my definition of acceleration, I know that the acceleration is really the change with respect to time, the derivative with respect to time of the x component of the velocity. So this expression is equivalent to what I started with, and all I'm going to do is rearrange these little differential elements. So basically I'm going to take the dt, and instead of pairing it up with the dv, I'm going to move it over so that now it's paired up with the dx. So here's my new expression. And so a couple things you notice here. One is I've changed what I'm integrating over. So rather than integrating over position, I'm now integrating over velocities. I've had to go through and change my my endpoints for my integral. And now I've also got this term dx dt, which I recognize as the velocity. So notice my dx dt term on this next line, right? So dx dt is just the x component of the velocity. There's my little differential element in terms of the x component of velocity. The mass will assume it's constant, and so we'll pull it out of the integral. And so this is what I'm left with. And so if I want to go ahead and do that integral, well, this may not look like something we know how to deal with, but if I were to replace all these velocity terms with x terms, we probably would recognize that, oh, the integral of x dx is nothing more than 1/2 x squared. Well, this is the integral of v dv, so it's going to be nothing more than 1/2 the velocity squared. So I've still got my mass term out front. My antiderivative here is now 1/2 of the x component of velocity squared, and I need to evaluate that at the two endpoints that I've got for my integral. And so when I do that, I end up with 1/2 mass times the final velocity squared minus 1/2 mass times the initial velocity squared. Well, this term is nothing more than the final kinetic energy of my object. My second term is nothing more than the initial kinetic energy of my object, because I know the kinetic energy is calculated as 1/2 mv squared. So k final minus k initial, well, final minus initial, that's just another way of saying the change in kinetic energy, and so I can denote that as delta k. So the third way that I can talk about the net work is through the work energy theorem. And so the work energy theorem tells me that the net work is equal to the change in kinetic energy. So what is that really trying to tell us? Right? It's easy to say that the work energy theorem is the net work is equal to the change in kinetic energy, but what on earth does that mean? And so for starters, there are a couple ways to think about this, but one is, well, let's see. So if the net force acts on an object has a component that points in the same direction as the object's displacement, well, we know that in any case when the force and a displacement point in the same direction, that force does positive work. So if the net force points in the same direction as the displacement, that means that the net force does positive work on the object. And if the net work is positive, that means delta K has to be positive too, which means that you have increased the object's kinetic energy. So when the net force and the displacement point in the same direction, that works to increase the object's kinetic energy. If, on the other hand, the net force and the displacement point in opposite directions, so just like with any work term, if the force and displacement point in opposite directions, then I know that the work done by that force is negative. So when the net force points in the opposite direction of the displacement, that means the net work must be negative, which means you have decreased the object's kinetic energy. If the net force does no work on an object, then there's no change in the object's kinetic energy. So basically what all this is trying to tell us is that we can think of the net work as how energy is transferred to or from an object to change its kinetic energy. So the net work will tell you how the kinetic energy of an object is changing. Right? If the net work is positive, then the kinetic energy has to be increasing. If the net work is negative, the kinetic energy has to be decreasing. If the net work is zero, the kinetic energy of your system, of your object, isn't changing. All right, so let's think about a particular example. So that's all that was sort of in general, and in general that's all true. So let's sort of try and make this a little more concrete by talking about a particular example. So for this particular example, let's think about a block. So here's a block, it's sliding down some inclined plane, and so at this particular instant, this block has a velocity vector. Here's its velocity v. We can think about this in a couple of different ways. So how the block's speed is changing, we can think in a couple of different ways. One is we can think in terms of the stuff we've been doing with Newton's second law. So let's think about sort of our Newton's second law formulation for how the block's speed is changing. So what we're going to do is we're going to let this block slide down, and then at some instant we're going to start pushing back up along the incline with some applied force. So the block will be sliding down, we're going to start pushing on the block back up the incline, and so we're interested in how the block speed changes once we start pushing. Well, from a Newton's second law perspective, we would say, well, we need to draw the free body diagram. I know that the block is going to accelerate along the plane, so I need to think about how the forces sum along the plane or perpendicular to the plane. The normal and the applied force, normal's perpendicular to the plane, applied forces along the plane. The weight needs to be broken up into those two components so that I can now think of those things along or perpendicular to the plane. And so again, we know that since the block isn't accelerating off the plane or into the plane, that Newton's second law says that means that the y component of the net force has to be 0 here, which means that the magnitude of the normal's got to be equal to this component of the weight. Then thinking about the acceleration is basically saying, well, how does this force, the applied force that we're pushing on the block, relate to this component of the weight? So the component of the weight along the incline. And so we've got three options. The first one is, well, if this force is larger than the downward component along the plane of the weight, then I know that when I add them together, I'll have a net force that points up the incline, which means the acceleration will point up the incline. And if the acceleration points in the opposite direction of the velocity, then that means that the block will slow down. The final speed somewhere down here will be less than the initial speed when I first start pushing. If, on the other hand, I switch it up so that this force isn't very large, and in fact that it's smaller than this component along the plane of the weight, then I know the net force will point down the incline, which means that the velocity and the acceleration now point in the same direction, and so the block will speed up. Now, it wouldn't speed up as much as if I didn't push at all, but if I don't push hard enough, then the block will still continue to speed up because the net force will still point down the plane, and so the acceleration and velocity will still point in the same direction. My third option, of course, is, well, what if I push with exactly the right force to balance out the component of the gravitational force that points along the plane? In that case, if these two things balance, then the net force would be 0, which means the acceleration would be 0, and if the acceleration is 0, that means that the block travels at a constant speed. So its velocity won't change. So all that is the way that we could have talked about this problem from our Newton's second law perspective. There's a couple ways that we can now think about the work-energy theorem and see what it's trying to tell us. So the first way, let's go back to where I've got a large force. Well, we already said if I've got a large force so that its magnitude is larger than the component of the weight pulling the block down the incline, then I know that the net force will point up the incline. The displacement, of course, is down the incline. And that the block's going to slide from up here to down there. So as it slides, if the net force points in the opposite direction, then this means that since the net force and the displacement point in the opposite directions, the net force does negative work on the block. And by doing negative work on the block, that means that we have to have a decrease in the block's kinetic energy. So this is a situation in which the block will slow down. To decrease its kinetic energy, it's got to have a smaller final speed than its initial speed. If I push with a very small force, so that again, that force is now less than the component of the weight pulling the block down the incline. Net force points down the incline, which means that the net force now points in the same direction as the displacement. This means that I'm doing positive work on the block, and I increase the kinetic energy. So here's a situation where the block speeds up. Again, it's not going to speed up as much as when I didn't push at all, but it's still going to speed up because this force isn't as large as the component pulling the block down the incline. If I pick exactly the right force so that the net force is 0, right? So my applied force cancels out the component of gravity pulling the block down the incline. My net force being 0 tells me that, well, 0 work is done on the block So the net work is 0, which means the kinetic energy doesn't change, which means my block travels down at a constant speed. So notice I get exactly the same answer, thinking about it in our Newton's second law way and thinking about it using the work-energy theorem. Now we said as a general rule, we're not going to want, when we're doing calculations, we're not going to come back and do the net force first. We're going to think about the work done by individual forces. So the other way that I can think about what's going on here is to say, well, when I look at my free body diagram, my displacement is down the incline. The normal is perpendicular to that, so I know that the normal is not going to do any work as the block slides down the incline. The gravitational force has a component that points down the incline, so it's going to do positive work. And the applied force points opposite the displacement, so it's going to do negative work. So the normal will do no work, the weight will do positive work, and the applied force will do negative work. If I have a very large applied force, so its magnitude is larger than this component of the weight, then the negative work done by the applied force will be larger than the positive work done by the weight. Which means, again, the net work, when I add up 0 plus this positive term plus this negative term, if this term is larger, that means I'm going to have a negative net work, which means I have a decrease in kinetic energy, which means that the block is going to slow down. If my applied force is very small, so notice, the signs don't change. Normal still perpendicular to displacement, applied force still points opposite the displacement, gravitational force still has a component in the direction of the displacement, so the signs don't change. But by changing the magnitude of this applied force, I've changed how much work the applied force does. So if I have a really small applied force, now the negative work done by the applied force is less than the positive work done by gravity. So when I calculate the net work by adding these three terms now, since the weight does more positive work than the applied force does negative work, I have a positive net work, which means I increased the kinetic energy. Again, increasing the kinetic energy tells me that the block sped up. If I have just the right magnitude of the applied force, so that its magnitude is the same as this component here, then the signs are all going to be the same, but gravity is going to do the same amount of positive work as the applied force does negative work. So when I add these three work terms up now, I'm going to get 0 plus the same number where one's positive and one's negative. These three things are going to add up to be 0. So my net work is 0, which means the kinetic energy doesn't change, which again means that my block is traveling at a constant speed. So the work-energy theorem conceptually is giving me the same information as what Newton's second law did. What we'll end up seeing is that same information, as a general rule, is going to come with an easier calculation because I don't have to do a vector problem. So to summarize, again, the net work can be positive, negative, or 0. If the net work is positive, that means you are adding to the kinetic energy of your object. It's got a larger final kinetic energy than it had initially, which means your object is speeding up, and that happens because the net force points in the same direction as the displacement. Your net work is negative when it is subtracting kinetic energy. Right? So the net force is taking kinetic energy away from the system, which means that your initial kinetic energy was larger than your final kinetic energy, and your object is slowing down. Again, this happens when the net force points in opposite the direction of the displacement. And then no work, so you're not changing the kinetic energy. Kinetic energy is the same at the beginning as it was at the end, which means you're traveling at the same speed at the beginning as you were at the end. And there are a couple different ways that you can do this. So one is you can have no net force, you can have no displacement, you can have the net force be perpendicular to the displacement, or you can have a situation, there's actually a fourth possibility, where the net force does positive work along some portion of the displacement, but the same amount of negative work over the rest of the displacement. So that again, when you add that up, you still get 0. So this table basically summarizes what the work energy theorem is trying to tell